Hello everyone. It's my pleasure to invite Professor Madhavan Swaminathan. He's the head of the Department of Electrical Engineering and is also the William E. Leonhard Endowed Chair at Penn State University. He also serves as the director of the Center for Heterogeneous Integration of Microelectronic Systems, which is the CHIMES. This is an SRC GEM 2.0 center. Prior to joining Penn State, he was the John Pippin Chair in Microsystems Packaging and Electromagnetics in the School of Electrical and Computer Engineering, and also a professor in ECE with a joint appointment to the School of Materials Science and Engineering, and also the director of the 3D Systems Packaging Research Center, which is a graduated NSF Engineering Research Center, ERC Center at Georgia Tech. And prior to Georgia Tech, he was with IBM working on packaging for supercomputers. Professor Swaminathan's interdisciplinary research on semiconductor packaging and systems integration over the years have resulted in more than 650 technical publications and over 200 invited presentations. He has written 3 books, 5 book chapters, 31 patents, 35 Best Paper and Student Paper Awards, 5 GT Awards and 2 startups, and several international recognitions, with the recent one being the 2024 IEEE Rao R. Tumala Electronics Packaging Award, which is the highest technical field award in packaging. And this is for the contributions to semiconductor packaging and system integration technologies that improves the performance, efficiency, and capabilities of electronic systems. He is also the founder of the Electronics IEEE Conference on Electrical Design of Advanced Packaging and Systems. This is the premier conference sponsored by the IEEE Electronics Packaging Society. He's a fellow of IEEE, fellow of the National Academy of Inventors, fellow of Asia Pacific Artificial Intelligence Association, and has served as the distinguished lecturer of the IEEE Electromagnetic Compatibility Society. He serves as an advisor to the India Semiconductor Mission and also on the external advisory board for Move to Terahertz. This is an EU initiative as well as advisor to 3DGS and Claros. He received his MS and PhD degrees from electrical engineering from Syracuse University, USA. So it's my pleasure to invite Professor Madhavan Swaminathan. The stage is yours, Madhavan.
Thanks, Ajay. Thanks for that introduction. And it's certainly a pleasure to be here. And the title of today's presentation is The Future of 3D Heterogeneous Integration, what we refer to as 3DHI. I want to share some of my thoughts with you. I've been working in the advanced packaging area for more than 30 years. And I think for the first time, packaging is taking the front seat in terms of how electronic systems need to be designed in the future, as well as to be able to be implemented in the future. So I'm with Penn State University, and formerly I used to be with Georgia Tech. So let me start with the disclaimer. So I'm going to be using some images. Please note that these were generated by ChatGPT. There's some data in those images. You know, sometimes it's not very accurate. We all know ChatGPT sometimes can make mistakes. The important part is to focus on the trends rather than the data itself when it comes to these ChatGPT images. So with that, let me get started. I'm sure all of us are familiar with Moore's Law. And lately, there's been a lot of discussions as to whether Moore's Law is really dead or not, and can Moore's Law be continued? And I'm going to share my thoughts with you on that, because that sets the stage for the rest of the presentation. So if you look at Moore's Law, we know that the number of transistors have been doubling every 2 years. And one of the nice, interesting things about Moore's Law is that it's been driven by economics. And as a result of that, if you look at the cost of the transistor, it's been decreasing from one generation to the other. And part of the reason is because of lithography, we've been able to shrink the size as well. The cost of a transistor used to be $7 way back in 1965. That was a discrete transistor. Today, the cost of the transistor is less than maybe a nanodollar or so. Now, if you look at the semiconductor industry, it's been driven by transistor performance. And every time there's been a bottleneck, there has been an innovation coming from the semiconductor industry to be able to address that innovation. But interestingly enough, in 2022, there was an inflection point where the cost of the transistor started going up. And part of the reason is because of yield-related issues, as well as the amount of capital investment you need to build transistors that are extremely small, let's say less than maybe 5 nanometers or so. So the question is, what do we do moving forward? And that is where we believe continuing of Moore's law comes in. For the last 6 decades, Moore's law has been driven by monolithic integration. But now we are entering the chiplet era, where instead of your transistor performance, you need to start looking at system performance. And the way you make that happen is through this chiplet innovation that allows us to continue the economics associated with Moore's law. And how do you go about doing that? So if you look at 3D heterogeneous integration, I give 2 examples of that. One is NGMM. This is out of the Texas Institute for Electronics, supported by DARPA, called Next Generation Microelectronics Manufacturing, that you're trying to stack chips on top of each other. And the second is what we are trying to do within our center called CHIMES, where we are trying to use a combination of 2.5D and 3D integration to be able to build these future 3D HI-based systems. So let me put this in context, and this is where ChatGPT comes in. So if you look at the number of AI data centers worldwide, what we refer to as the hyperscalers in 2024, there were a total of around 366 of them. And in the United States, there was around 122. But this year, 2026, the expected number of these AI data centers worldwide is expected to increase to 466. And if you look at the United States, that's going to be at roughly around 132. So the reason I show this is because there is a crisis emerging. And if you look at the amount of power consumption by these AI data centers compared to the regular data centers, that is increasing from around 4% to around 12%. And what is even more important is that in the United States, the amount of energy consumption by these hyperscalers is increasing at roughly around 4x compared to the amount of electricity that is being added to the grid. And there was a recent Wall Street Journal article which says that the problem begins with fluctuating computational loads that gulp down energy for artificial intelligence operations, such as training these machine learning models. So there are 3 challenges to be addressed. One is the power generation itself, because if you look at the way it's being done today, make use of these gas turbines, it becomes very challenging. There appears to be a movement towards other types of power generation sources, such as the small modular reactors, the SMRs, coming from the nuclear energy side. The second issue is the location of AI data centers. So I'm in the state of Pennsylvania. There's a governor's race going on. And there is a debate over these AI-driven data center development and its impacts on energy, environment, and communities. Because nobody wants to have an AI data center, a hyperscaler, in their community. And finally, building efficient system, chip, and software architectures, what I refer to, or what we refer to as the infrastructure. And that is what I'm going to focus on today. How do you build these systems that are highly efficient such that it doesn't consume a huge amount of power? So why are AI data centers so energy hungry? So if you look at this figure here, and if you look at the amount of compute that you need to be able to train a large model, it is multiplying at roughly around, or increasing at roughly around 750x every 2 years. And if you look at Moore's law, basically the number of transistors we are able to integrate on a single chip, it's only doubling every 2 years. So there is a huge gap between the two. And the question is, if you truly want to build these systems, you have to be able to use many chips, which means that you have to worry about how to move the data between these chips, and as well as being able to do it in a very, very energy efficient way. So what can you do? So if you look at how data centers are built today, you have a bunch of transistors that you connect together to build these deep neural networks. And when you run out of these transistors on a single chip, you start connecting these multiple chips to each other, shown here as GPUs. And when you run out of GPUs on a data center, you start connecting data centers to each other. So the need of the hour is, can we build this giant monolithic GPU? And the answer is no, because there is a lithography limit which limits the size of the largest possible GPU to around 800 millimeters squared. In addition to that, one of the challenges that we have is the memory wall. This is the third bottleneck, where the memory density is only increasing at 2x every 2 years. And we know that these AI systems need lots of memories and other dies in close proximity. So the question to ask ourselves is, can the AI server node in the data center be re-architected to make it more efficient? So this is an example of an AI data center, or a schematic of an AI data center that consists of racks. And within the rack, you have a tray. And think about trying to re-architect that tray shown here as the AI server node. So that AI server node consists of the GPUs, consists of the CPUs for data preparation, it consists of the HBMs for your memory, but along with that, you have other technologies such as power delivery, embedded cooling, photonics, etc., to make sure that it actually works and you're able to build these highly efficient systems. So given this AI server node, question is, what can advanced packaging actually do? So if you go back to the late 80s and early 90s, one of the challenges that we always had was the length scale difference between the interconnects that we could have within the chip as well as outside of the chip. So roughly between 80 to 90% of the volume of the system came about because of packaging. And the reason for that is the length scale difference between on-chip and off-chip was of the order of roughly 1 million or so. So since then, things have changed. And if you look at some of the previous years, we've been able to make significant advances with front end of the line silicon, shown here as silicon CMOS, the back end of the line silicon, as well as the package. However, each were made advances as separate blocks, and we ended up gluing these blocks together, making the interface between the blocks as the primary bottleneck. So moving forward, if you look into the future, it's all about heterogeneous integration. And what is it? So think of Lego blocks that you are able to connect to each other laterally as well as vertically in such a way that all these interfaces disappear. And that brings us through 3D HI, the 3D heterogeneous integration, which is a means to continue Moore's law by interconnecting a diversity of transistors and integrated circuits components, blurring the line between on-chip and off-chip. That alone is not enough. It should include the integration of new and transformative logic, memory, and interconnect technologies to support these AI workloads, and should enable seamless data movement at high energy efficiency. And this is the focus of the center that we have called CHIMES. This is a technological hub for 3D HI. There are a total of 18 universities involved, with Penn State as the lead. And you also see our sponsors, some of the largest companies in the world, semiconductor companies, are basically supporting this effort through SRC as well as DARPA. And these are the many faces of CHIMES. So we have roughly around 27 PIs in the center, as well as more than 100 students working on various aspects of the problem. Now we have an exemplar driving the center, shown here as the future AI server node. It's a notional embodiment that capitalizes on heterogeneous integration. So what does it consist of? So think of a GPU that is surrounded by HBMs to ensure that the distance between the GPU and the HBMs is very, very small so that you can move the data between them. Then you take this as a tile and you repeat it many, many times on a large substrate in such a way that any GPU can communicate with any other GPU or any other HBM over here. In addition to that, you have the CPUs, the new memory devices, and other types of accelerators that you try and embed beneath these GPUs in such a way that you're able to create a cross-section of a package that is shown over here. So at the top, you have the GPUs and the HBMs. At the center, you have your CPUs and other types of new memory devices. And at the bottom, you have your voltage regulators for power delivery. And you're trying to put them all together using some kind of a core material with these redistribution layers on either side. And you're also adding new materials into it that allows you to pull the heat out. In addition to that, you're also trying to bring in photonics to be able to connect these chips to each other. And at the end of the day, you're basically building that tray, which is the AI server node, that's able to support large amounts of power. And between the chips at the top and the printed circuit board, you have just the substrate. There is no interposer. And if you look at the two major challenges we have to make this happen, one is power delivery, the second is thermal management. So how do you go about doing that? So let's look at data movement. If you take an AI server node, it consists of chips. These chips can either be next to each other or on top of each other. So you want to be able to connect all of these chips to each other. In addition to that, you need to be able to connect these racks, these trays to each other within a rack, as well as to be able to connect these data centers to each other. So that requires different types of interconnect technologies, and there are 5 of them I've listed over here. The first is copper wiring. Copper wiring is extremely good over very short distances. You can make use of these massively parallel IOs to be able to move the data around. Once you go over longer distances, you cannot make use of copper. You have to go to wired RF, that is shown over here. To go to even longer distances, you need integrated photonics. And then between these AI server nodes, you need co-packaged optics. And finally, over very long distances, you need your fiber optics as well. Now, as I mentioned earlier, data movement alone is not enough. You have to combine that with energy efficiency. And you need to do that across length scales when you connect these chiplets to each other. So if you look at this figure here, the vertical axis represents a very important metric, which is the product of the bandwidth density with units of terabits per millimeter or millimeter squared times the energy efficiency, which is the reciprocal of picojoules per bit. Energy efficiency represents the number of bits that you can transmit and receive between chips for 1 joule of energy. X-axis represents your length scale that goes to more than a kilometer. If you look at copper, as you can see, they're very, very good over short distances because you have 2 types of losses with copper, one coming from the conductor, the second is the dielectric. When you look at RF, you remove the conductor, you can work with dielectric materials to move your data around. So it gives you a little bit more, a higher kind of a metric when it comes to distances anywhere between, let's say, a centimeter to a meter or so. Then you have the integrated photonics that you're trying to make use of within that AI server node or the substrate that gives you a very large metric that is shown over here. Then you have your co-packaged optics and then your fiber optics. And the key message over here is if you can start embracing large size substrates or large size packages such that you're able to pack a large number of these chips, the GPUs, the CPUs, and the HBMs all together, then you have an opportunity to be able to maximize the product of this bandwidth density and that energy efficiency. So just imagine there is, sometime in the future, an entire rack can basically be mapped into just a tray that is shown over here, or a package. And this was actually put together by a system architect who works heavily on the memory side of things, Professor Tahana Rosing. She is the director of another Jump 2.0 center called PRISM. And one might say that this is something that appears to be too futuristic. But if you look back, I remember way back in the 1990s at IBM, we used to build these supercomputers. And the amount of power, compute power that we had in that supercomputer, today you are able to get that on a smartphone. So something like this indeed is doable, assuming we are able to make good advances both on the front end of the line transistors as well as on the packaging side. So there are 5 critical metrics that we are using to drive the center. Metric number 1 is on power delivery. You see the goal, the SOTA, state of the art, the gaps, as well as the challenges. I'll go through the details shortly. The second metric is the performance. The third is the form factor. How large of a substrate can you actually build? Fourth, of course, is the cost. And the fifth is the reliability. And let me go through each one of them in a fair amount of detail in terms of what some of the challenges are, as well as the technologies that we are developing. So let me start with power delivery. So the goal over here is to be able to support GPUs that are able to consume more than, let's say, 2 kilowatts of power at very high current density. And how do you go about doing that? Because you want to do this at a very, very high efficiency, greater than 90%. Now, the manner in which we define the efficiency over here is the ratio of the power that is delivered to the transistors to the power that goes into a voltage regulator module. And we know that one of the challenges we always have are these I squared R losses. And the way you reduce these I squared R losses is to try and bring this voltage regulator as close to the GPU as possible. In addition to that, you have to support this using this voltage conversion, what we refer to as these integrated voltage regulators, or IVR. So what we are trying to do within Chimes is to develop this technology shown as integrated vertical power delivery that allows us to reduce these I squared R losses while supporting these high conversion ratio integrated voltage regulators. So how do you go about doing that? So let's look at the power delivery from the grid. So you have an electric grid. So you convert from AC to DC, and then finally you provide the voltage to the GPU or the CPU at a voltage level of around 0.8 volts. Now, if you are following what NVIDIA is trying to do, we are trying to move away from a 400 volts over here to 800 volts to be able to bring that power as close to the rack as possible. And the reason for that is to reduce the copper losses. In addition to that, when you reduce the copper losses and you're trying to move your power at a high voltage, you can reduce the cross section of your copper cables as well. Now, the question is, what do you do going from 800 volts down to 0.8 volts? So this is where the voltage conversion comes in, because you have multiple options. You can convert from 800 to 48, 48 to 0.8, or 800 to 12 down to 0.8, or 800 to 6 to 0.8. And what we are trying to investigate within Chimes is to understand what the trade-offs are for us to be able to make something like this happen. And the way we are trying to look into this is by using a distributed network of these voltage regulators to be able to power these GPUs similar to what is shown over here. And what that requires are fairly advanced switching technologies like gallium nitride, being able to embed your inductors in your capacitors, etc., along with a package that provides a vertical power delivery with minimum losses associated with it. So that brings us to this whole concept of integrated vertical power delivery, as is shown over here, where you have the GPUs at the top, you have your switches at the bottom, and in between, you have your capacitors and your inductors. These are the flying capacitors, that's the output capacitors, and these are the inductors. So these are basically bulk regulator circuits. And the way you can go about doing this is by creating this modular architecture, where if you look at the bottom side of this processor, each module, let's say, carries 100 watts. 20 of these modules gets you the 2000 watts you're looking for. Now, the efficiencies we have been able to achieve so far is roughly around 88%. It's not good enough because we want to go up to upwards of 90%. And if you look at where the losses are coming from, they come from the switches as well as the inductors. And the way you can improve those the efficiencies is by making use of low voltage GaN to be able to reduce the drain to source resistance, as well as coming up with technologies for inductor integration that we are currently working on. Now, I mentioned capacitors. Now, there are multiple ways by which we can integrate capacitors. So one of the things we are trying to look at are these deep trench capacitors, as opposed to these multi-layer ceramic capacitors, where you take these capacitors and just embed these into cavities in the substrate, the package, and then you start building your layers on top of it. This is the actual fabricated device that is shown over here. And as you can see, these are multi-terminal capacitors, where we've been able to embed capacitors of the order of around 14 microfarads. And after embedding and packaging, you're looking at ESL, equivalent series inductance, of between 0.1 to 1 picohenry at around 1 gigahertz with an ESR of between 2.8 to 3 milliohms. Now remember, I also mentioned you need to somehow blur the interface between what is on-chip and off-chip. So we are also working at trying to embed transistors into the back end of the line wiring of the chip using these amorphous oxide semiconductors shown as AOS. Two examples are shown over here. One is the DC to DC converters that becomes part of the backside power delivery network on the chip, as well as being able to address the memory wall by integrating these ITO gain cell memory as part of the back of the line process. The second is the performance, being able to go vertical. Now, all of us are familiar with hybrid bonding. So clearly, hybrid bonding allows you to go to very fine pitch. The question is, are you able to stack chips on top of each other that comes from different technologies, not the same? As well as, how do you address the thermal management side of things? Because when you stack chips on top of each other, heat will get trapped. We're trying to address both of them. The first one through these reconstituted wafers or panels, where we reconstitute a wafer using multiple chips from different technologies before we do the stacking. And the second is being able to introduce these heat spreader materials such as aluminum nitride and diamond in between these layer stacks, such that you can spread the heat out and pull the heat out from the edge. We've also been looking at embedding these chips. So if you look at the vertical distance over here between the chip that's embedded and the chip that is on top, that length is very, very tiny, of the order of around 30 micrometers or so. So with that, we've been able to show that indeed you can send data at a very, very high speed at a bandwidth density of roughly 2 terabits per second per millimeter squared at an energy bit per bit of around 35 femtojoules per bit. So if you look at the product of the two, you end up with around 60 terabits per second per millimeter squared per picojoule per bit. Now, I mentioned integrated photonics. Integrated photonics is a little bit different compared to co-packaged optics. Co-packaged optics, you make use of a fiber. And part of the reason for that is you're trying to connect multiple AI server nodes to each other. So because the cross-section of the fiber is much, much larger than the waveguides in that substrate, you end up using multiplexing. So what you do is you take data, you serialize it, then you modulate it, and then you do use wavelength division multiplexing to send it through the fiber and do the reverse on the other side. This modulation, along with the serialization and WDM, tend to be very, very energy hungry. Think of a scenario in the substrate where the fiber is replaced with many, many parallel waveguides, optical waveguides. And since you're doing it over short distances, you can get rid of the WDM because each of you have enough of these waveguides over here so that there is no need for multiplexing. And as a result of that, you get rid of the serializer as well. So you can do that based on this glass substrate technology where you can embed waveguides into different layers of this glass and use that as a way to connect these chips to each other. So here are some early results. How do you create this? So we make use of a laser to be able to write these photonic waveguides. And you do that by varying the energy output of the laser as well as the depth of focus. So if you look at the structure here, this represents the cross-section of glass where we have 4 layers of these optical waveguides. And you can imagine, you can try and make these waveguides even smaller so you can get huge amount of density over here. And then you start doing your routing based on crosstalk rules, similar to what you do with copper. So these are the massively parallel photonic interconnects as opposed to the copper interconnects that carries the data. So let's see how that actually looks like. So you can start looking at different types of topologies to be able to connect these chiplets to each other using photonic waveguides across the cross-section of glass. And if you look at these numbers here, it tells you the length over which you're trying to do that communication or that routing, and the losses are indicated over here. These kinds of losses are impossible to achieve with copper. And in addition to that, if you look at our metric, you have the bandwidth density times the energy efficiency also shown over here. And that number becomes very, very large, similar to 3D integration using copper, but over much larger distances. And you can also show that by making use of something like this, you can actually get a fairly nice eye. This is NRZ 25. So that's the 25 gigabits per second, where you can show that the bit error rate can be less than 10 to the minus 15, similar to what you get with copper. So let's look at the substrate core itself. And one of the core materials we've been making use of is glass, and this is what I've been showing you in some of the earlier slides. So why glass? So if you compare glass with silicon, it has properties very similar to silicon. At the same time, it's a little bit different compared to silicon. And we all know with glass today, we can basically create routing on both sides and connect the two together through these through glass vias that are shown over here. But you can go one step further. Remember, I mentioned chip embedding in glass, right? So you can do that. That increases the functionality of the substrate core. You can also add photonic waveguides in glass, similar to what I showed you, that increases the functionality even more for that core. Now, one of the nice features of glass is that you can control the coefficient of thermal expansion of glass that allows you to improve the reliability of these glass substrates as well, similar to what is shown over here, where you can optimize the CTU of glass along with the metal layers on both sides, such that you're able to maximize the fatigue life at the interface between the chip and that substrate and that printed circuit board. Now, if you compare glass with silicon, one of the issues we have is the thermal conductivity. Thermal conductivity of silicon is at 148, glass is at 1. The question is, how do you pull the heat out? So before I get to that, let me talk about form factor and cost. Now, instead of a silicon wafer, if you start working with a glass panel that is 500 millimeters on a side, you have more area to work with. So if you're able to manage the yield, then there is a possibility that you can build these large size substrates at lower cost. Now, one of the challenges is the warpage, the thermomechanical reliability, which is very much connected to or related to the thermal side of things. And what is shown over here is the actual measurement that we have made when we were trying to work with a 150 millimeter size panel. And as you can see, even though there is warpage, it can be managed and it can be controlled reasonably well by developing a process that allows you to manage this issue. So let's now come to thermal management. So if you look at our goal, we want to be able to remove a background heat flux of 2 kilowatts per centimeter squared, along with a hotspot as high as 30 kilowatts per centimeter squared. Now, if you look at the cross section that I showed you, the dies at the top, I can pull the heat out from the top side because these are flip chip. Similarly, when I add the voltage regulators on the bottom side of that package, I can make use of a cold plate to remove the heat as well. Question is what you do with the chips in between. And this is where microfluidic cooling comes in, what we refer to here as embedded cooling, where our goal is 500 watts per centimeter squared. In addition to that, when you're trying to stack chips on top of each other, I mentioned aluminum nitride. Another material that we're working with is polycrystalline diamond that you can deposit at a fairly low temperature. And here, the issue is how do you make sure that you're able to not only spread the heat out this way laterally, but also be able to create these thermal vias that are electrically insulating, but thermally conducting. So here is an example of an evaporator architecture we're working on. So this is to pull the heat out from the top side, and it makes use of two-phase cooling, liquid vapor separation that is indicated here, where we've been able to demonstrate a heat transfer of roughly around 1.2 kilowatts per centimeter squared. It's, I think, one of the highest that's been shown so far for these kinds of architectures. So we make use of this capillary action through micro grooves as a way to pull the heat out. And we make use of two types of liquids. One is water. The other one is this HFE that is shown over here. Now, I mentioned aluminum nitride. So how do you deposit aluminum nitride? Now, the issue is when you're trying to deposit aluminum nitride, deposition alone is not enough. You also have to do it at a very high speed. And that is what is indicated here. So we've been able to demonstrate that indeed you can deposit this aluminum nitride at a temperature of roughly 400 degrees centigrade at a fairly high speed that gets you a thermal conductivity of roughly between 100 to 115 watts per meter Kelvin with film thicknesses of around 1.5 micrometers. So let me now come to embedded chiplets, the microfluidic cooling. Now, when you're trying to embed these chips, the question is, can you remove the heat from these chips using these microfluidic channels that are shown over here, while at the same time connecting these chips to chips at the top, for example, a GPU here versus a CPU over here, such that you have signal transmission between the two. So that requires a technology that allows us to create these copper vias over here that are part of this microfluidic channel, shown here as thermal vias, while at the same time you have vias that carry the electrical signal that are thermally insulated. So we've actually been able to build something like this. So these are devices that are shown over here that are, you don't see the die, sort of see the die here because it's embedded. And then you have, it's embedded in glass with these RDL layers on either side. And you have the microfluidic channel in it that is removing the heat where the fluid is making contact with these copper pillars. And what we've been able to show that is that we've been able to get to a heat flux of 500 watts per centimeter squared while keeping the chip temperature at around 80 degrees centigrade. And the way you do that is by controlling the flow rate that is indicated here. And we've been, once again, been able to show that you can keep those thermal resistances fairly small by controlling that flow rate, while at the same time ensuring that the differential pressure between the inlet and the outlet is kept to manageable levels. Now, when you're trying to introduce microfluidics in glass, you're also working with different types of materials. So you have to address the thermomechanical reliability associated with it, the stress and the strains that you're actually creating because of the CTA mismatch between these materials. And this is where we believe machine learning comes in, can be very, very useful, where we've been able to do lots of simulations to try and understand exactly what these stress and strain levels are. We've also been able to demonstrate the reliability of these channels, microchannels, by running this for around a week, 7 days, non-stop. And we've been able to show that indeed you can keep that chip temperature constant while at the same time ensuring that the differential pressure is within manageable levels. We've also done this with two types of liquids, DI water and PG25, which is a glycol mixture that is used to pull the heat out. And just one slide on EDA. So we all talk about multi-physics simulations and the importance of it. When you're trying to build systems like these, that is becoming even more critical. And once again, as I mentioned earlier, machine learning can really help. So we've been working with PIN, what we refer to as the physics-informed neural networks, that allows us to look at various designs and design geometries that combines mechanical, thermal, and electrical to be able to predict the signal integrity. So with that, let me quickly switch to application to communications and sensing, because this is another area we're working on where a lot of the technologies that I showed you can be very, very useful. So if you look at communications, you're looking at MIMO type of communications where you're making use of beamforming, as well as if you're trying to do sensing, radar types of applications, you're trying to generate these very narrow beams that is able to differentiate between a small object and a large object. Now, these are examples of computing at the edge. And when you're trying to do that, what you want to do is to be able to communicate with the environment seamlessly, while at the same time being able to do all of the computations at the edge, along with bringing intelligence into that scenario as well. And that's what we refer to as the antenna to AI platform, where the front end is basically RF and the back end is your computations that includes the AI accelerator as well. So how do you go about doing that? So this is where we believe advanced packaging is a key enabler. So here is an example of 2.5D integration where we take glass, we embed chips in them. These could be the indium phosphide power amplifier chips or the beamformer ICs. We can also embed the AI chips in it, build your redistribution layers on either side. The top side has the antenna and package, so it's looking into the sky. The bottom side has the thermal management solution, both the microfluidics as well as the air cooling solution. You can also do vertical stacking, glass on glass with RDL layers with the antenna and package at the top, and then you rely on these thermal vias to remove the heat from the bottom side. And recently, this is an area we've been working on for some time. Recently, we were able to demonstrate a 200 gigahertz transmit receive chip all embedded in the glass module. So if you look over here, so this is your glass. You have the embedded chip here, RDL layers on the top, the antenna resides over here, and the bottom side connects to a heat sink to pull the heat out. And if you look at this entire module here, this tiny part that you see inside of that circle is the actual module. So this is your transmit chip that is embedded, and this is your antenna all integrated in the package. These wire bonds that you see over here connects to this control board over here that has the DC bias in it as well as the control lines. So all of the high frequency signals reside inside of the module. And you see on the bottom side, you have this huge heat sink to pull the heat out from the bottom side. And we have been able to show communication over a distance of 7 meters at a very, very high speed. And you see the EVMs. This is for QPSK as well as the 16 QAM. And if you look at the Gen 1 link performance, you get an improvement of roughly by around 30%. So the 32 gigabits per second, if you use standard packaging technology for 16 QAM, can be increased to around 44 gigabits per second. So with that, let me try and conclude so that there's enough time for questions. Just closing thoughts, and these are estimated by ChatGPT. So please take it with a pinch of salt. But having said all of that, if you actually do the calculations and try to figure out how much energy you're saving to train a 1 trillion parameter model using the technology that I described, that savings is anywhere between around 50 to 80%. And that amount of savings is equivalent to powering 90 homes per year, 90 homes per year in the United States. So that is substantial. As you can see, this is for a single 1 trillion parameter model. Just imagine how much energy you can save when many of these models are being trained. So with that, thank you so much for listening. Please take a look at our website. The link is shown over here. We also have a newsletter that you can subscribe to if you're interested. These are quarterly newsletters. With that, thank you so much for listening.
Thank you, Madhavin. Great presentation. Quite a plethora of results, starting from the substrate, no substrate, to glass, and then to the thermal management. Excellent.
Thank you.
Let me go to the audience.
Should I stop sharing, Vijay? Ajay?
You can continue to share because
Okay.
there could be some questions that
Sounds good.
someone may be asking.
Sure.
Let me go back to the audience. I mean, are there any questions from the audience? It seems the audience is quiet. Let me ask a question.
Sure.
So you showed one of those slides where you are connecting those chips directly to the PCB without any substrate, but then a subsequent slide showed the core packaged optics that require the interposer to be added. So how do you build between these two heterogeneous integration system?
Sure, sure, Ajay. So first of all, all the slides that I showed you, these are not interposers. These are all substrates. Because if you ask yourself the question, why do you have an interposer to begin with? It is because you're using a material that is different from, let's say, the printed circuit board, and therefore you need another kind of a substrate material to act as the buffer to be able to go from the chip to that printed circuit board. So that adds an extra layer of packaging, right? So what we are trying to do here is to eliminate the interposer altogether. So that requires rethinking this whole concept from first principles, and that's what I showed you. So the photonic waveguides, we are not trying to create this on top of the glass core. It is inside of that glass core, where the glass core, along with the polymer layers on either side, represents the substrate.
So the glass core itself is a substrate. So when it comes to
Yeah.
the electronic integration onto those substrates, so you'll have a larger panel, and then it will be a
Correct.
separate region where you will be embedded. You will be adding those electronic part.
That is correct. So large panel, the chips on top, you have the chips at the bottom, chips in between, and then right where the glass core is, you can also create those photonic waveguides.
Okay.
Yeah.
Can you hear me?
Yes.
So I had a quick
Yes.
question about interposer. So
Who is this? Who is
this
that?
is Uma Jha from
Hi,
University of
Uma.
Florida. So I had a question about interposer. Interposer serves at least two purpose. One is trying to really connect two very high speed interconnection between, for example, CPU and memory. That's what is mostly used for. Secondly, is also try to really spread out the signals across much wider area than it could come from a chip, because the chip could be very, very small, the diameter and the TSV may be very small, and then you want to connect it to the substrate or PCB, you have to spread it out. So is that not a correct thinking?
No, I think you're right. But ask yourself the question, the interposer by its very name, right, is something that you're trying to place between a substrate and a chip, right? And ask yourself the reason why you're trying to do that. You're trying to do that because you have very fine density of lines on that interposer that doesn't match well with the printed circuit board, and therefore you need to go through an intermediate layer like a package substrate to be able to get onto that printed circuit board, right? That's number one. Number two, the interposer may not be large enough for you to be able to accommodate all of those chips. And therefore, you're trying to connect these multiple interposers together in some way through your printed circuit board, while at the same time ensuring that your reliability is fairly good, because there is a mismatch between, let's say, the interposer that you're trying to create using silicon and that printed circuit board. Now, if you can find a way to merge that interposer and the substrate, the interposer and the package, right, that resides between the chip and that printed circuit board, right, then you start seeing benefits, because not only can you connect these chips to each other, with very high density connections, you also have a way by which you can remove one level of packaging. So that is the thinking over here in terms of what that package ought to look like to make something like that happen.
So let me add one more thing,
Sure,
Dr.
please. Yeah.
Swaminathan. So if you talk about chiplet and vis-a-vis 2.5D connectivity, so how would you do if you kind of get rid of interposer?
Oh, it's actually, so if you look at, let me go back to my apologies. Let me flip these.
No problem. Sorry.
Okay. No, that's okay. Let me see if I can find that figure. Okay, so let's take this figure, right? So this figure, each GPU, let's say, is a chiplet, right? So you are connecting these two GPUs through these redistribution layers here, right? Similarly, you're connecting the HPM to the GPU through these redistribution layers here. So this is your glass core, right? So communicating from the top side to the bottom side through these TGVs. One of the nice things about glass is these TGVs do not have a lot of parasitics associated with them. So these interconnects can also be high speed. So you establish all of that connectivity in the substrate such that you don't need that interposer anymore.
Thank you. Thank you for explanation.
Okay. Sure.
Yeah, thank you, Ma. There is a question here. It's more of a logistical question, I guess.
Sure.
And it's asking about the supply chain issues, and probably not very relevant to this presentation. The question is about research. Most of the chips are coming from Taiwan. And is there any concern for the future of continuing the research because of the geopolitical situation?
That's, I think, a very, very good question, because, we always, when we thought about the supply chain, we said the materials came from Japan, okay, the substrates, the chips came from Taiwan, the substrates maybe came from China or some other place, and we used to put everything together. Things are changing quite a bit, okay? And I think this is a very valid question to determine what the supply chain ought to be and where are the supplies going to come from. Okay. Now, having said that, this work started many years back, more than 10 years back, in terms of trying to look at glass as a means for packaging. And since that time, I think the supply chain has come together reasonably well. Still not there. Okay. There are still challenges. And then with chiplets, as you know, when you have chiplets each coming from a different source and each from a different process, you need to have the right protocols such that they can communicate with each other, the standards. And those standards are beginning to emerge. But my feeling is, if you truly believe in a technology like this and believe and realize that we are going to be getting into this energy crisis, I think we better figure out a way to address this. Otherwise, very soon, every one of us is going to be in trouble.
Thank you, Malvin.
Sure.
Thank you for the question as well. So I have another question, which is with respect to the vertical power delivery. So you showed that the interfacial chip is the capacitor that you place between the gallium nitride and any other AI chip that you have.
Sure.
But now, besides the capacitor, what is also important is the inductors. And these inductors are very large. And maybe one inductor is not sufficient enough. I mean, probably the form factor of those inductors overpowers the form factor of the chips and also, for the semiconductor chips, which essentially means that you will require multiple integration, multiple vertical inductors embedded between these chips. I mean, how and thus the efficiency may not be that good, or I mean, have you looked into it?
Yeah. I think once again, a very, very good question. Now, if you look at this cross section here, right, some of these dimensions are drawn to scale. So you see the inductor is very tall, right? Because if you make use of a discrete inductor, it will not work because it's too tall. Sometimes it can be thicker than the entire package itself, right?
Correct.
And so there are two things that you need to think about. One is, can you develop an architecture that allows you to reduce the amount of inductance that you actually need so that you can miniaturize these inductors? So that is the first thing that is shown over here. If you look at this architecture, the amount of inductance you need is around less than around 2 nanohenries per phase. That's number one. Number two, having said that, you do not want to have these discrete inductors here. These have to be thin film inductors. So thin film inductors, the way you miniaturize it is by using magnetic materials. The problem with these magnetic materials is, as you know, is the saturation current. Okay. So therefore, today, if you look at the reason why our losses are still quite high, one contribution comes from that inductor. And we have to figure out a way by which we can develop these low loss magnetic materials that also are easy to integrate as part of this cross section that is shown here. There is still work remaining. Yeah?
Oh, okay. Thank you, Mathur.
Sure.
Is there any more questions from the audience? Oh, Lavanya has a question.
Hi, Professor Swami. This is Lavanya.
Sure.
So the question I have is, from a manufacturing perspective, what are the biggest challenges in adopting glass in the silicon process flow? What do you foresee?
Yeah, I'm going to give you a single word answer: reliability. That is the issue because, with glass has come a long way. Don't get me wrong, right? But having said that, we're yet to see a product, okay, that is related to AI type applications. And the reason is because, when you create these TGVs in glass, you start seeing cracking because there is an interface between that metal copper and that glass that creates problems. And it appears to me at this point in time that that is the major showstopper. If we can figure out the reliability aspect of things, you're going to see lots and lots of products with glass. This is less of an issue for other types of applications like communications and sensing. But it's a larger issue for AI because you're trying to work with larger size glass, glass with larger thickness. You need higher aspect ratio of these TGVs, creates problems.
Thank you. So the form factor does make a difference in introducing
It does.
glass.
It is not that, it's very hard to be able to build these large size substrates, right? So it requires a lot of thinking and figuring out how to address that reliability issue.
Okay. Thank you, Professor Swami.
Sure.
Thank you. And let's once again thank Professor Madhavan Swaminathan for this excellent talk and also for all the question answers that he has.
Thank you so much for listening.
Thank you.
Wonderful meeting all of you. Take care. Bye-bye.
Greta, you can, okay. So can we go to the next slide? So we have some open slots for the technical seminars. And we are looking forward for any from the audience who want to give us the talk as well. Thank you so very much.